Next problem, we are given that these small circles have a radius of 1. This is a big circle, this whole thing is a square, and it asks us what is the length of the side of the square. So what I'm going to first do is solve for what is the radius of the circle. Now for these type of problems, it usually is helpful to draw lines from the center of this circle to where it touches something important. So here I draw to there. Also from the center of the circle I'm going to draw from there. I'm also going to draw in this line. And let's also draw on that one. And then I can also draw on that. Okay, I kind of already know which lines are the most important. And then what we usually do is we use Pythagoras to solve for the radius of the circle, or we use Pythagoras just to get some sort of constraint. So let's say that the radius of the circle is x. Then this length over here will be x. This length over there will be, this part over there will be 1. If I draw in, if I extend this line over here, we get something that's going to be perpendicular to this line. This height over here is 1, so that height over there is going to be 1. This whole length was x, so therefore this part of the length is going to be x minus 1. And now we just have to find out what this length is. We know that this whole length over here is x. This whole length over here is just going to be 3. So this part is just going to be x minus 3. And now we've just got that x plus 1 squared is equal to x minus 1 squared plus x minus 3 squared. And we just have to solve for x. And then multiply by 2 to get the length of the side of the square. Let's just do that. We've got that this is going to be x squared plus 2x plus 1 is equal to x squared minus 2x plus 1 plus x squared minus 6x plus 9. Here this is going to just be x squared minus 10x plus 9, which is just going to be x minus 9 to x minus 1. Quite clearly, here's this would just be 0 once I take that to the other side. Quite clearly, x cannot be 1, so that means that x must be equal to 9, and that means the side of the square must be 18. How certain am I that x cannot be 1? Well, what I can do is I can try and figure out how to draw this when x is 1. We will get that, let's first draw the big circle and the square around it. It will be like this. And then let's draw these little circles. This little circle has also a radius of 1, so it will be on top of this circle. This little circle also has a radius of 1, so it'll also be on top of here. Then we've got 2 circles over here, which will also be on top of this. That circle's on top of this. That circle's on top of this. And we'll get that all of the circles in this thing are all going to be on top of this one. Now let's just reread through the question to see if that's disallowed. 12 small circles with radius 1, large circle inside. Okay, it says small circles and large circles, so that kind of implies that the big one must be a different size than the small ones. And it's tangent to only every small circle touches only two other of the circles. So that makes this weird degenerate case impossible. Whenever we've got something like this, it's called a degenerate case because everything just goes like in the extreme. So we've got question number 7. For question number 7, we've got this right angle triangle with given side lengths. We've got this perpendicular line here. Then we've got these two in circles over here. And we are asked what is the ratio of the area of the smaller circle to the area of this larger circle. If R1 is the radius of the smaller circle, then its area is going to be pi R1 squared. The area of the larger circle, let's say its radius is R2, so its area is going to be pi R2 squared. The pi's cancel, so this becomes R1 squared divided by R2 squared, and this just becomes R1 divided by R2 squared. Now, usually for these type of questions, well, the most mechanical way, the way that goes using, that solves this in the way that's most similar to similar types of questions, the most mechanical solution would be first to find this value of R1, and then to find this value of R2, then to divide these two together and square it. And I'm going to look at that later, but there's a shortcut in this question. The shortcut is we've got this ratio. Now technically for a ratio we don't need to know what is the individual values of R1 and R2. We basically just have to find something that has this ratio in it. And one way to now we have to ask, where do ratios appear in geometry? One place ratios appears is this. If you've got two triangles with the same height and shared base, then you've got the ratio of the bases is equal to the ratios of the areas of the triangles. Another place where ratios occur is if you've got two triangles that are similar. Okay, then there will be ratios between their sides. Now for two similar triangles, the way it works, well, there's many ways to describe this, but one way to describe it is we pick one's length of this triangle and we divide it by a length of that triangle, and this will be equal to, let's just write that, a divided by a prime. This will be equal to any other length of this triangle, even if it's the length of the radius of inscribed circle, divided by this corresponding length of this triangle. Let's say it's the length of the radius of the inscribed circle. Basically, if these two are similar, then all ratios of lengths are preserved, because similarity just means that this is just a bigger version of that. Now usually with similarity we would work with the sides. So if this is side length B and this is side length B prime, then B divided by B prime is the same as A divided by A prime, but we can use any lengths. When you work with something like this, where you've got this is a right angled triangle and this is a perpendicular drop from this, you'll know that this triangle is similar to this triangle, is similar to the big triangle. But let's just prove that. Let's suppose this angle over here is just some value. Then this angle is just going to be equal to 90 minus that. This angle over here is also going to be equal to 90 minus that. in this triangle, and this angle over here is just going to be 90 minus that, but that was just 90 minus this, so it's just going to be that. So we've got that for this triangle, it has the same angles as this triangle over here, which means they are similar. So to calculate the ratio of the in radius of this one divided by the in radius of this one, R1 divided by R2, this is just going to be equal to one of the sides of this triangle divided by the corresponding side. So it would be equal to this length, BP, divided by the corresponding side length of this triangle. Now, the way similar triangles works is we just have to look at the corresponding sides, or the sides that are opposite the same angles. So BP is opposite this angle, and we have to look in this triangle the side opposite this angle, which is PC. Or we could use the length AP, that is opposite this angle, which is going to be in this triangle, the side length opposite this angle is BP. Or we can use the side opposite this 90 degrees, which is just AB, divided by the side opposite this 90 degrees, which is BC. Whenever you get a problem like this, you must just figure out which one of the ratios is the easiest to calculate, and the ratio that's easiest to calculate is basically this one because it's given, divided by this one because it's also given. And so we get this as 8 over 15, and to answer the original question we just have to square this. R2 squared is going to be equal to 64 divided by 225.